All right, with chapter 3, I'm making another video, some of the problems that got left off of the last video. So they're not in order. You'll have to refer to both videos to get all the problems. So problem number 1. A reaction between reactant A, blue spheres, and reactant B, red spheres, is shown in the following diagram. Based on this diagram, which equation best describes the reaction? All right, so obviously the blue atoms are together in some sort of molecular form, and the red one is an individual atom. So you've got the molecule blue reacting with the monoatomic atom red to form a one red, two blue compound. So this looks like A to me. Glycerin is an amino acid used by organisms to make proteins. Is represented by the following molecular model. All right, so write the molecular formula. So I see 2 carbons, 1, 2, 3, 4, 5 hydrogens, 2 oxygens, and the blue one's a nitrogen. So the convention is when you're writing organics, carbon goes first, hydrogen goes second, oxygen goes third, and anything else, chlorine, nitrogen, whatever, goes last. So this would be the correct way to lay out the molecular formula for an organic compound. All right, determine its molar mass. All right, so I add up the atoms. I've got 2 carbons weighing 12 AMUs apiece, 5 hydrogens equaling 1 AMU apiece, each oxygen 16, 14 for the nitrogen. When I add them up, I have 75 atomic mass units, and that's for one molecule. So if I collected 6.02 times 10 to the 23 molecules together, the beauty of Avogadro's number is I'd have that exact number, that exact mass in grams. So 75 AMUs per one molecule, 75 grams per mole of the molecule. C, calculate the mass of 3 moles of glycerin. All right, so now that I know what the molar mass is, right, that's for 1 mole of glycerin. If I've got 3 moles of glycerin, I can use the molar mass as a conversion factor to go from moles of glycerin to grams of glycerin. So when I multiply across, moles cancel, and I'm left with how many grams I'd have if I had 3 moles. Calculate the percentage by mass of nitrogen and glycerin. All right, so we know that if I had 1 mole of glycerin, it's 75 grams. And out of those 75 grams, you've got 1 mole of nitrogen, which would weigh 14 grams. So this is going to give you a mass ratio, right? Grams of nitrogen to total grams. Multiply by 100 to turn that fraction into a percentage. And that would be the percentage of nitrogen. Let's change that. We wanted nitrogen. Nitrogen. Better. Okay. 7, nitrogen, N2, and hydrogen, H2, form ammonia, NH3. Consider a mixture of nitrogen and hydrogen in the accompanying diagram. All right, so blue spheres are for the nitrogen, the white ones are for the hydrogen. Draw a representation of the product mixture, assuming that the reaction goes to completion. How did you arrive at your representation? What is the limiting reactant in this case? Okay, so with this in mind, I kind of blew this out, right, so I can put things together. Here's my number of, here's nitrogen reacting with hydrogen. All right, so if I'm doing the balanced equation, right, N2 molecules reacting with H2 molecules, ammonia, the formula for ammonia is NH3. All right, so when I balance this, I would need 2 in front of the ammonia, right, so I'd have 2 nitrogens going in, 2 nitrogens represented by the 2 ammonia coming out. And that gives me 6 hydrogens coming out, so therefore I'd have to put a coefficient 3 in front of the hydrogen. All right, so what this means, stoichiometrically, is I would need 3 times the amount of hydrogen per nitrogen in order to make 2 moles of ammonia. So in the picture, if you count them up, you've got 4 blue ones and 9 white ones. So I ask myself the question, doesn't matter which one I ask. I asked, if I have 9 hydrogen, is that enough hydrogen to burn up the 4 nitrogens? So I do a conversion, right? According to the balanced equation, for every 3 hydrogens, I need 1 mole of nitrogen. I would need 3 moles of nitrogen to burn up that 9 moles of hydrogen. Do I have it? Yeah, they gave me 4. All right, so they gave me 4, and all I need is 3. So that means that nitrogen's in excess and that hydrogen's the limiting reactant. All right, so now I can go forward with, how much ammonia is going to be formed. All right, so I'd end up with 1 nitrogen left over, 1 nitrogen in excess. So when this goes forward, right, if I'm going to do this reaction, I've got to break those bonds between the nitrogens, break those bonds between the hydrogen molecules. Go back again, right? So there they are together, right? They're bonded. I've got to put energy in to break those bonds, and now I'm going to release energy when I match up 3 of those hydrogens to each of the nitrogens. And lo and behold, I've got 1 nitrogen left over. So this reaction only goes as far forward as I have hydrogen. The reaction stops when the hydrogens are used up. What scientific principle or law is used in the process of balancing chemical equations? Answer, we balance chemical equations because of the law of conservation of mass. So whatever goes into a reaction atom-wise has to come out of the reaction atom-wise. In balancing equations, why should you not change the subscripts in the chemical formulas? Answer, because you change the compound. All right, the subscript gives you the number of atoms combined together in the molecule, or the number of ions surrounding each other in the ionic compound. How would you write out liquid, water vapor, aqueous sodium chloride, and solid sodium chloride in a chemical equation? We use brackets around italicized versions of lowercase l, lowercase g, lowercase aq, and lowercase s to indicate that the state that the the compound or the element is in. Write the balanced equations write the balanced chemical equations to correspond to each of the following descriptions. Solid calcium carbide reacts with water to form aqueous solution of calcium hydroxide and acetylene gas. All right, so they gave us the formulas for calcium carbide and acetylene gas. So really, the trick with writing chemical equations is getting the formula right. So if you know the formula for calcium carbide, right, it's plus water. The arrow indicates change, forming calcium hydroxide. Brackets around the hydroxides, plus acetylene. And once you've got the formulas correct, then you go back and balance, all right, to get the right number, same number of atoms going in as coming out. B, solid potassium chloride is heated and decomposes to form solid potassium chloride and oxygen gas. So again, getting the formulas correct. Potassium matched up with the chloride ion, potassium ion, chloride ion, and oxygen molecule. And then you go back and use coefficients to get the same number of atoms going in as coming out. Zinc reacting with sulfuric acid to form hydrogen gas and zinc sulfate. The beauty of a chemical equation is you don't have to write all that out, right? I just have a short expression where the reactants go in, chemical change occurs, and the products come out. So D, when liquid phosphorus trichloride is added to water and reacts to form aqueous phosphorus acid, they gave you the formula, they didn't have to do that, and aqueous hydrochloric acid. So get the formulas right for the reactants, get the formulas right for the products. Once you've got the formulas correct, then go back with coefficients and balance. and hydrogen sulfide gas, or if you were talking about it as it's gas, is passed over iron 3 hydroxide to form iron 3 sulfide and water. Put the coefficients after you get the for the formulas in for the reactants and the products. Write the balanced chemical equation for a reaction that occurs when magnesium reacts with chlorine. All right, so we know that magnesium is going to form +2 charge, chloride forms a -1 charge, so it's going to be a 2-to-1 ratio in the formula for the product. So this one's a little more complicated, right? They're not giving you the product here. You'd have to deduce what the product's going to be between magnesium and chlorine gas. And balance, right? This one's balanced. B, barium carbonate, get the formula right, decomposes to form barium oxide and carbon dioxide gas. Get the formulas right for barium oxide and carbon dioxide gas, then go back and balance. Didn't have to balance there. C, when styrene CH88 is combusted in air, that means reacting with oxygen. Predict the products. Guys, anytime you're combusting a hydrocarbon, you're always making carbon dioxide and water. And the trick to balancing this is to look at the hydrocarbon, right? You've got 8 carbons going in. Balance the carbons first. Then look at the hydrogens. Balance the hydrogens second. And then go to the oxygens, right? So really, this is the trick to balancing these combustion reactions. Sometimes it can be difficult, so be systematic about it. Balance the carbons, then the hydrogens, and then the last thing you do is balance the oxygens. All right, so I've got 16 plus 4. I've got 20 oxygens coming out of the reaction. Therefore, I'd need 20 oxygens going into the reaction, oxygen atoms. You've got dimethyl ether combusted in air. Again, it's the oxygen in the air that's reacting. You're forming carbon dioxide and water. Balance the carbons first, balance the hydrogen second, and then go to the oxygens. Don't forget, you've got that oxygen sitting there in dimethyl ether, right? So 7 oxygens coming out, 7 oxygens going in.